Hi there everyone, welcome to another Chem Complete lecture. I am Professor Tomney, and let me just say this lecture is a long overdue one, and it has been requested by many people over the past months. So today we are finally going to continue the HPLC series, and we're going to learn about the next HPLC phase typing, which, believe it or not, is known as normal phase. And with such an uninspired name, and its very basic sounding terminology, you would think that we should have covered this at the start of the HPLC lectures. But some of our prior lectures on things like reverse phase and ion-based HPLC came first because they are actually more common than normal phase HPLC is. Okay, so before we get into this, remember that info for anything I'm discussing here will be referenced down in the description box, including a link to my personal website at chemcomplete.com. You can always go there to check me out. And the HPLC playlist. So some of the terminology we might be using here may be a little confusing if you're just jumping into normal phase and you don't have some of the back reference, especially the first two lectures, which was kind of the intro to HPLC, as well as the HPLC basics for columns and understanding columns, how they work, and some of the features with that. Okay, so as always, I appreciate all the love and support that you guys have shown. And I do have some exciting news. I'm going to be finished with my Introduction to HPLC guide later this month. So if you are viewing this video in late August of 2021 or at some time beyond that, there should be a link down in the description for the guide. And you can still always go over and look at the previous guides that I have produced at chemcomplete.com. And that's an excellent way to support my work. And remember that always just liking any useful content you come across and engaging with the channel is support enough already. And I love all the support that you guys have given me. We're well over 10,000 subscribers now. So welcome back to the channel, and let's take a look at this. So as far as normal phase HPLC, we're going to discuss a couple of things. So what is normal phase HPLC, and why do we actually call it normal phase? It's a bit bizarre, right? And we've got the normal phase columns and solvents. We want to have a discussion about that. How are they different from some of the other things that we've come across so far? How are they similar? Something called localization action. This is a very important concept in chemistry in general, but it is especially important when you start talking about adherence to stationary phases and columns. So we'll talk about that. And then we obviously want to know, when should we be applying normal phase chromatography in comparison to some of the other methods. And then finally, we usually like to wrap up with some kind of pros and cons or advantages and drawbacks to using normal phase chromatography. So we're going to take a look at each of these individually. All right. So first of all, what is normal phase HPLC and why do we call it that? Well, the reason that it's called normal phase HPLC is that it was originally it was the first way that HPLC was utilized or implemented. Okay. So if you followed this lecture series so far, you may remember that reverse phase HPLC was one of the first methods that we really talked about after column basics and stuff like that. And so the name here, when it says normal phase HPLC, this setup was originally the HPLC conditions used and developed prior to the development of reverse phase HPLC. So that is the reasoning behind the quote-unquote normal name. Okay, so it's usually considered a secondary option to reverse phase. So, and we'll talk about that more soon. Reverse phase tends to be the one that is prioritized for research and development, even though normal phase came first. But that's why it's called normal, is it was the first one present. And then reverse phase was developed sort of with the reverse conditions compared to the normal phase HPLC. So understanding that, right, normal phase HPLC is going to utilize a polar stationary phase or a polar column. Okay, so if you remember in the discussions revolving around the reverse phase HPLC, we had the opposite set up with a nonpolar column. So we were talking about things like C18 columns with these long hydrocarbon chunks that would sort of be modified onto a silica base. Whereas now we are talking about a polar column instead of a nonpolar column, right? So this is going to be a polar column, which again, we're talking about the stationary phase of the separatory process is polar in normal HPLC. Okay, now in counter to that, our mobile phase is going to mostly be comprised of nonpolar solvents, right? So this is the liquid that we will be moving through to mobilize the analytes through the column. And these are going to be relatively nonpolar, whereas again, in the reverse phase, which is the more common technique utilized today and more prevalent in the literature, the reverse phase used primarily polar solvents, with water kind of topping that list. Water, generally speaking, is a big no-no in the normal phase HPLC, especially if you're dealing with something like a bare silica column, because then if you don't have those modifications, the water can kind of almost act as a modification. And we'll talk about that in the pros and cons section. But you do have to be kind of more aware if you're going to have water present. And obviously water is present in our everyday environments. We're talking about residual moisture and things like that. You have to be aware of that when you're using normal HPLC conditions, where it might not be quite as critical a concern or consideration when you're dealing with reverse phase HPLC. Okay, so let's break this down further. So column-wise, we said you're going to be sticking to polar options. So one of the best known options, okay, for the columns, and let's just label that here. We'll say this is columns. So one of the best options that we have for columns is going to be the bare silica, or sometimes this is called non-modified silica-based column, right? So just your classic silica column without any type of modifications, I should say. So this is similar to actually many large-scale benchtop columns that are used for large-scale purification in laboratory practices. So I remember back when I was in graduate school, I was doing organic chemistry, right? You would produce your synthesis, or you would create your new compound, and then there would usually be side products or leftover starting material if it wasn't completely efficient in conversion or whatever, and you had to separate the materials out to purify your bulk product to take it to the next step in the synthetic process. And one of the things we would utilize was silica columns. It was very, very effective at kind of on a larger scale, larger than HPLC, separating out grams of material, right? Hundreds of milligrams to grams of material at a time could be used with this benchtop type of process. And most of the solvent options were primarily non-polar. So, you know, you were talking about your hexanes and your ethyl acetate mixtures. Maybe you threw in a little tiny bit of methanol, a couple drops or something to help with the polarity. But generally speaking, it was a non-polar approach from the mobile phase. So coming back to this, not just silica, but there are other options that we could use for modifying a silica base. Okay, so some of the functional groups that you might come across for this could also include things like cyano columns. Okay, so this would be when you have some sort of a cyano, which is also sometimes called a nitrile, okay, modification onto a silica column. And we did talk about or see some of this sort of stuff towards the bottom edge of the reverse phase, right? So with reverse phase, it was kind of like, all right, C18, C8, C4, and then if that still wasn't working, maybe you could start kind of dabbling in the cyano adaptations, right? So if you wanted to get a little more polar than that, you could get something like a diol modification. So di meaning two and ol meaning alcohols. So this would be some sort of a column that the silica base would have an adaptation that has two alcohol groups, right, attached to it. That's obviously extremely polar. You think of the structure of water and how polar water is. That's going to give you a lot of polarity on that mobile phase. And then we can also deal with amino groups. So you could consider right? Some sort of a NH or some sort of an NR, where R is probably a small hydrocarbon, not very large, otherwise we're starting to talk nonpolar again. And those would be some of the base modifications that you could do to these types of columns. And you would get varying degrees of polarity and therefore varying degrees of retention and interactivity with the analytes that are coming across. All right, so then let's talk about solvents. So for normal HPLC, the solvents are primarily nonpolar, as we've discussed a moment ago. So the most common, certainly that I've come across, is usually hexane. Now there's a couple others that you could potentially use. Some people do, in special cases, use fluorinated solvents, but hexane tends to be a more common choice, at least from what I've seen. And hexane is usually going to be kind of the primary solvent that you would be using. It would make up the bulk of what you're using most of the time. And that's because it is very nonpolar. It's just a strict hydrocarbon without any type of polar functional groups or modifications there. Okay, and then you're going to have other options that you can kind of utilize and couple with your base or your primary solvent in order to offer like sort of small bumps in polarity. So an example of this would be ethyl acetate, which I mentioned a minute ago. Okay, ethyl acetate is a very common solvent that's used in conjunction with hexane, and you kind of mix the ratios together, try different percentages. A lot of this will be trial and error, but then you see what you can come across and what you can find that sort of optimizes the retention and the separation for what you're interested in. Okay, another example is methylene chloride, sometimes referred to as dichloromethane, depending on the name that you're using. Okay, and chloroform could be kind of ranked in here with this, but some of the chlorinated solvents offer good choices. You have to be careful when you're handling them, really all of these, but the chlorinated ones tend to have toxicity or carcinogenic concerns associated with them, right? So this, for example, would be CH2Cl2. Chloroform would be with 3 chlorines and 1 hydrogen there. But those do offer kind of an optimal chlorinated solvent that's not too polar, but does offer a little bit of a polarity bump if you're mixing it in with some of the others. Okay, some of your other ones, now you have to start being a little more careful and selective when you're picking these out because we're starting to get more and more polar. Ethers and acetonitrile. Now, if you remember, and you go back to the lecture on the reverse phase, acetonitrile and ethers were actually at the bottom of that solvent list. And that solvent list was the reverse of this. So it said, okay, water is one of the go-tos, and that's usually your primary one. And then you have your alcohols, methanol, ethanol, things like that, right? Then you have acetonitrile, and then you have ethers. And ethers were kind of like, okay, this is middle of the road polarity. And that's generally where we stopped in that reverse phase lecture. Well, now we're coming here and we're saying, okay, start very nonpolar, hexane, ethyl acetate, right? And then we cap out, this is considered the more polar end, right? Mid-level polarity for the normal phase. So you're kind of seeing, right, a meeting in the middle where ethers and acetonitrile can sometimes cross over into both types of HPLC techniques. And then on the cusp or the outer edges are those extremely nonpolar or polar solvents that are usually reserved. And that's not to say you might not have a small bit of methanol or something like that thrown in some of your normal phase. But generally speaking, you're sticking more towards these that are going to make up the primary targets for your solvents in a mobile phase, in normal phase HPLC. Okay? So, with these options nailed down, we now want to ask ourselves, how does normal phase HPLC work on sort of a mechanistic or a practical level? So starting with the loading and separating of multiple analytes, you can expect that analytes with polar functional groups are going to have strong interactions with the column or the stationary phase. And that's because that column or stationary phase is also polar. So this is primarily going to be due to intense intermolecular forces. So we're going to, this is a very common concept out of general chemistry. We're going to abbreviate IMF, right? But if you imagine that you've got sort of this silica-based level, right? And then let's just say we'll go with a diol, for instance, right? So you've got this diol modification that's coming off of here. when you have other polar components, so let's say something that's got a hydroxyl group, right, coming across here, you are going to have a very strong interaction between the partial positive hydroxyl and the partial negative associated with the diols. And you're going to, almost like a intermolecular glue, you're going to get an interaction here with the column. And the column's going to want to hold on to this analyte and keep it there, right? Those forces are very attractive. And so the job of the mobile phase, as the mobile phase is coming along here, it's trying to slowly push, right, these interactions along the column until we can finally elute off the other side and you start collecting. And the elution rates, or the retention times, are different for each of these compounds based on their polarity and how strongly or weakly they are going to interact with the stationary phase in the column. So this is the technique, or I shouldn't say technique, but the phenomenon of localization. So we were talking about in the beginning localization action, and this is sort of that being conceptualized on an image level, okay? And it is important to conceptualize this because this is essentially how you are going to be separating your analytes in the column. So the more polar analytes are going to adhere to the column longer, and they'll have higher retention times. This allows you to plan and predict how things are going to kind of separate out if you're setting up a normal phase situation. Okay, so again, this phenomenon of intermolecular adherence to the column is often referred to as the process of localization, okay, in which analytes are going to localize or stay in one area of the column and then will kind of be separated through the elution of nonpolar solvents, maybe with some slight increasing polarity if you try to do like a phase gradient sort of thing. Okay, you have to, if you're going to kind of do like phase gradient HPLC, you need to make sure that your solvents won't demix, that they will stay mixed thoroughly when you're doing that. Sometimes that can be a larger concern when you're on the nonpolar end. Okay, but the nonpolar analytes, we would expect them to come off of the column first, and then the more polar analytes with that localization or adherence are going to be coming off the column last, as far as retention time is concerned, okay? So when a non-polar mobile phase is used, it easily moves the other non-polar analytes off of the column, giving them earlier retention times. And then oftentimes slightly stronger polar solvents may be needed to kind of slowly break apart the localization and usher it along in the process. So many times several different solvent ratios or combinations will be required for a little bit of a trial and error discovery process, like I stated earlier, or research and development, whatever you want to call it, right, in order to optimize the separation and the resolution of the HPLC results, because this is what you're working with here. You need to move these along in a fashion, right, breaking apart the localization at a sufficient enough rate that you're not going through boatloads of solvent. It doesn't take 20, plus hours just to do a small load or a small run. But you also need to consider you don't want to wash everything off of the column all at once and not get any separation at all by adding something too polar, like, spiking it with 50% methanol or something like that. That's far more likely to be an appropriate mixture when you're talking about reverse phase HPLC instead of normal phase. Okay, so this is kind of the action, the mechanism of action and how this works. So knowing this, it still stands that reverse phase and many of the ion phases that we mentioned sort of at the beginning of this lecture are used over normal phase HPLC. They are preferred methods as far as trying to deal with these sort of separations, right? When research and development needs to turn to something, usually reverse phase is the favored, and if there's something very polar, then maybe ion separation is utilized in some form. Okay, so when is it appropriate to use normal phase chromatography? Well, it turns out that there could be several scenarios in which this technique is applicable, and that's what we want to take a look at or discuss next here. All right, so let's put sort of when to use normal phase, which I'll abbreviate NP, normal phase HPLC, right? So when is this appropriate? Well, there are a limited number of cases, but there are some. So number one, if you are going to be dealing with large bunches of primarily hydrocarbon based. And I say primarily because obviously if there are certain functional groups that are present that increase the polarity, that could change the situation. Okay, but some examples, right, of something like this could be if you take a look at a lot of the vitamins, right? So maybe something like vitamin D, which is kind of cholesterol based. Cholesterol is this big, bulky hydrocarbon steric molecule. It doesn't have a whole lot of polarity associated with it. That's why it's solubilized in a lot of fats when we talk about it nutritionally. Okay, vitamin A, if you take a look at retinol or beta carotene, which is kind of the prelude to vitamin A, it is very, very long conjugated hydrocarbon molecule. It's kind of this straight big chain. Okay, so vitamins, and again, if maybe you're taking a look at something like hormones, basically if something is cholesterol based, so it doesn't necessarily mean that it's cholesterol itself, although that is important, but if it is cholesterol based, which a lot of hormones tend to be, then it may be appropriate to use something like this. But the key is, if you've got large hydrocarbon molecules that primarily have a lot of CH groupings, okay, you're kind of steering away from a lot of the oxygens, the nitrogens, especially if those groupings have hydrogens on them. So hydroxyl groups or alcohols, amines, though now you're starting to get pretty polar, right? And so this will generally be a good method for separating these types of compounds. And again, having some polarity is not necessarily bad because it helps them with the localization, so they separate at different rates. You don't want everything to just wash off at once. But if you start getting very, very polar molecules, then that can become problematic because the localization is going to become so strong that it's going to be difficult to get decent separation. It's going to be all or none. They kind of glue to the column, or you put something in that's so polar that it just washes them all off. Well, it's not going to separate or offer you anything if it's just all sticking to the column and adhering there, or if it's all just being washed out and you basically get what you started with as far as the sample that you put in or loaded onto the column, right? Okay, so very often these compounds have poor solubility in polar solvents. So remember, reverse phase uses polar solvents, right? And so it can be next to impossible to load these compounds, and even if you're lucky enough to load them, moving these large hydrophobic compounds along something like a C18 column might be incredibly difficult, okay? So another situation which may seem extremely obvious, but is still something we want to mark here, is if reverse phase HPLC fails, okay? So if this is the case, usually what's going to happen, this is just reality here for a minute. Most people are going to go to reverse phase unless they have a very strong reason, like in example 1, and I'll give you another one, a third example here. But most people are going to go to reverse phase to start with, and there's multiple reasons for that. It's not just that the column is nonpolar and that the mobile phase is polar, but think about the cost base. If you're using water as your primary solvent for an HPLC system in comparison to hexane, and this is getting a little bit of a preview into the pros and cons category, obviously one of those is going to be far more affordable than the other, right? If I'm buying a lot of hydrocarbon specialty solvents in comparison to water or some of the mass-produced alcohols that tend to be a lot more affordable, that is something to consider, okay? And you have to keep in mind that when you're doing this, cost is a factor, right? So it's one thing to sit and talk about the theory, oh, this is how it works, and this is how you can separate, and these are how you optimize. But it's very different if you're, let's say, a medium-sized company and you are offering clients HPLC runs on a consistent basis to just turn around and say, oh, well, we'll just use tons and tons of hexane, right? Now, there's certain ways that you can kind of get around some of that. You can try to recover some of it, which is a pro because they have low boiling points. But generally speaking, you need to consider the amount of waste being generated, the bottom line in terms of your dollars. All of this can play into, right, something in relation to this. So what we have here, right, reverse phase HPLC fails, then normal phase may be a serious consideration after that, okay? And number 3, and this one's kind of interesting, okay, is that you can very often separate out geometrical isomers. Okay, so this is kind of a large category, but this is important because geometrical isomers can be very difficult to separate chemically because they have the same exact chemical components. They have the same oxygens and hydrogens, right? So think of something, so to give a kind of a sub-example here, right? Think of something like enantiomers, for those of you that have some background in stereochemistry, okay? So enantiomers are chemical molecules that are essentially going to be the non-superimposable mirror images of one another, right? And we know that this is important in the drug world. You have to be able to separate them out because they could have different binding receptors in the body, but it's very difficult if they have the same exact chemical functional groups and sort of chemical identity to be able to take them and separate them out and say, oh, well, I'll just solubilize this, set of enantiomers in a water and ethyl acetate extraction, because they're both going to go into the same phase. They have the same general chemical properties when you're taking a look at them. So that's having the ability to separate this out is very, very important. Okay, so to give you an example, let's take a look at a column bed where there's two different enantiomers and one may be separated out compared to another. Maybe not enantiomers, excuse me, but geometrical isomers. So give me a second and I will set that up. Okay, so to illustrate this example, let's consider a bare silica column this time. All right, so we've got sort of these silica-based functionalities that have the hydroxyl coming off it, right? That's the bare silica. And you can see this along with the diol columns. These are going to interact strongly with water, which again, I'm kind of previewing. Water needs to be handled with care in these types of environments. So you end up having a situation like this, okay, where you've got, right? So we've got the column. This is the stationary phase going this way. And if you take a look at this, let's consider two different compounds. So for one, we are going to have a para-chlorobenzene, or dichloro, right there. Okay, so para is a 1,4 positioning like this. Okay, and we're also going to consider its geometrical isomer, which will be the meta version. So we're going to do, here's chlorine and here's chlorine, right? So this sort of has a 1,4 substitution pattern, whereas this has a 1,3 substitution pattern. For those of you that may be a little far away from organic chemistry at the moment and haven't heard that in a while. Okay, but they are, right, the same number of hydrogens, carbons, chlorines present. They're just arranged in a different fashion. So you could see where this might become problematic when you say, oh, I'll just throw these into this type of extraction, or I'll separate them out by boiling or things like that. They are going to have very similar properties to one another. But what's interesting here is that when you put them on the column, kind of like when they go into a human body, enantiomers or geometrical isomers have the ability to bond in certain geometrical fashions, and therefore a lot of times they can be separated out if you have that selective binding capability. So if we have a situation, right, where we've got something that comes along like this through the column, that's a chlorine there, right, in the 1,4, well, this is just perfectly aligned, right? If these are partially negative, these are perfectly aligned to just have a nice interaction here, right, with the silica hydroxyl groups. However, all I have to do is change the chlorine to this position. And now all of a sudden, right, I don't have that interaction anymore. Even if I change it here, right, the alignment isn't going to be set up effectively there. And so it turns out that you could effectively separate a 1,4 versus a 1,3 isomer when you have the ability to localize certain geometrical isomers over others on these columns. And this is a huge advantage. So while there may be limited scope to normal phase HPLC, the ability to separate geometrical isomers should not be understated or undersold, because it, generally speaking, is very difficult to do. You need to have the ability to selectively bind to certain geometrical arrangements over others. Again, this is quite effective in living systems where certain enzymes can bind to or pick up one compound over another. But generally speaking, we don't want to be using expensive enzymes or cell lines or certainly humans, right, in order to go through and try to separate out and do these trials. So HPLC, normal phase, is effective at being able to do this. And that is something, again, that should not be undersold in terms of the benefits of normal HPLC. So then finally, what we're going to kind of do here is wrap up, because we're going on about half an hour for this one, and we're going to talk about some of the pros and the cons. So now that we know the groundwork for normal HPLC, how it works at the molecular level, and when it might be appropriate to use, we're going to wrap up the lesson with a compare and contrast regarding the advantages and disadvantages. So let's consider all of the advantages for a moment, and then we will talk about some of the drawbacks that could come with that, doing a pros and cons list. So some of the pros for normal phase chromatography are going to be the following. So this is our pro list here. Okay, the first one is that there's going to be a larger range of, and I'm going to abbreviate this here, hydrocarbon. Okay, so there's a larger range of hydrocarbon compounds that are going to be soluble in the solvents used, so the mobile phase. So this kind of goes back to the first point here, right? Which is that if you have very large hydrocarbon compounds, or any compounds that are primarily hydrocarbon in nature, without a whole lot of excess polarity, you are going to have difficulty using alcohols and water and some of the polar solvents used in reverse phase to solubilize them, load them onto a column, and move them through. So this is definitely a pro or an advantage of the normal phase. Okay? Now, one that may be overlooked sometimes is that because we're using these nonpolar solvents, the solvents that tend to be used here are going to have a lower viscosity. Now, viscosity is a chemical term that is used to sort of describe the flow, how thick a liquid is, okay? So we would say something is very viscous if it pours slow. So, for instance, maple syrup, okay? Whereas something is not as viscous if it pours very readily or rapidly, like water. But even within that, if you start looking at hexane and you start looking at ethyl acetate, a lot of the ethers, the hexanes, they are not as viscous as water and the alcohols. And that's because they don't have the same intermolecular forces that kind of bind them together or glue them together. And so when you get those weaker intermolecular forces, the viscosity goes down, meaning it's more free-flowing and it doesn't kind of plug up as easily. Okay, so why is this a benefit? Well, it's going to allow, okay, in turn, higher or increased flow rates without a problem. And why is that beneficial? Because you can move your system, your HPL system, quicker. You can move samples through it at a more ready rate. You can prep your columns and flush them at a quicker rate. Generally speaking, time is money. You save time when you're using less viscous solvents. Now, that doesn't mean that you always can, but in the case that normal phase works out, this is a pro, is that you're going to be able to kind of run your instrument at a higher flow rate, and the higher the flow rate goes, generally speaking, the quicker the run is going to be. Okay? So that's an important pro to keep in mind, kind of a practical one, because you're really talking about saving time in the long run if you're doing these techniques over and over again, day in and day out. All right? Okay, now another thing to consider is that, generally speaking, there's going to be a wide variety of nonpolar solvents. You know, there's still a decent variety of polar ones, but generally speaking, there are a lot of different ones that would be considered nonpolar up to mild polarity. And so when you have a wide variety of solvents that are sort of at your disposal for mixing and matching in these situations, you usually can have a high level of control or specificity over retention. Okay, and that can be beneficial because if you can manipulate your solvents, or you have a whole lot of them and you can kind of tinker with them and play around, if you have a high level control over retention, you can leave certain things on the column while removing others and getting a lot of distance between them to get very clean separation with your HPLC. So having a large kind of arsenal of nonpolar organic solvents is going to allow for a high degree of retention time selectivity and separation. And so that's a pro. Okay, one of the others, and I'm just going to kind of write this here, this is still a recap of what we had above, is that you can utilize this for geometric isomers. Okay, they tend to be difficult to separate out, and so having the ability to do this is really a pro or a positive in the normal phase system. Okay, and then one of the last things that's important, and this kind of balances itself out with one of the cons that we'll see in a minute, is that the solvents, generally speaking, because they're nonpolar, they're not as viscous, they don't have as strong of an intermolecular force, the solvents are going to have lower boiling points. And if you have solvents that have lower boiling points, they are usually going to be easier to recover. And that's important because when you talk about green chemistry, especially with these solvents that potentially are going to be damaging to the environment, damaging to the wallet, produce a lot of waste, you want to be able to recover them with a low boiling point to utilize them over and over again. Okay, so there are various devices. For instance, when I was in graduate school, this was on the benchtop level. We would use things called rotovaps, and they were basically round bottom flasks that would sit in a water bath, and you would set it to a very low or mild temperature. You'd pull a vacuum, and then it would remove the solvent system you were utilizing away from the analyte or the compound or the product, and then recondense it over a cold column with some antifreeze running through it, right? Chilling it down, some chilling solution, and then you could recover your solvent. And if you were using that solvent to run those columns on, let's say, a weekly basis, a daily basis, that solvent's very valuable to you. You want to recover it and be able to utilize it again, right? Instead of just throwing it into the waste. Obviously, if you're doing something that needs to be excessively pure, you might need to go through multiple rounds of this just to make sure that there's no analyte, especially if you have something that's a lower boiling point analyte, right, that's making it in there. But generally speaking, you are able to recover some of these solvents, which can help ease some of the burden on the pocketbook. Okay, so now some of the cons to wrap this up. And the first one is going to be kind of the opposite of the first up here. So while there's a large range of hydrocarbon compounds that are soluble in the solvent, normal phase is not good at dealing with polarity. Okay, so it's not good with, what I should say is it's not good with high polarity. Okay, so very polar functional groups, i.e. ions, right? We're going to need to be sticking more to reverse phase or even a subset of reverse phase like the ion pairing chromatography. Okay, so some of the reasons for this is that you've got high degrees of localization that are going to be difficult to break apart. So we talked about that, right? Localization. Okay, we're going to also have a poor ability to elute with the inability to use highly polar solvents. So generally speaking, it's going to be poor solvent elution in a case like that. Okay, so one of the other things you've heard me mentioning as we've gone out here is that water typically needs to be avoided. This is particularly, so I'm going to kind of put a star with this one. This is particularly, you need to be careful of this with the bare silica, because it can kind of set up and almost make it its own addition to the bare silica column with how strong the adherence can be. Okay, so water, generally speaking, needs to be avoided, and this can be difficult because to avoid water is, you're talking about moisture in the air, moisture that can get into your solvents, especially as you're starting to increase the polarity of your solvents. You need to make sure that they're kept very dry, right? Because you can certainly start getting water into some of your alcohols, into your acetonitrile. There's no reason that that can't absorb some of the moisture that's sitting around in the lab over time. So you need to be very careful to avoid water in some of these situations. And one of the reasons for that is that when the water kind of randomly combine throughout the column, this can start to produce unpredictable separation and unpredictable results. And when we start talking about unpredictable results, or in other words, results that are not going to be repeatable, that is a problem in science, right? We should be able to use the same solvent system, utilize it over and over again with the same column, and generally speaking, provided the column's in good health and has not been worn down too much, you should be able to reproduce your results as far as retention times. It shouldn't be spotty or changing back and forth on a day-to-day basis. Okay, and then finally, one last con to wrap it up, because we're now at 40 minutes here. Okay, the solvent cost. Okay, and we're going to put and environmental impact. Impact is high. Okay, so if you take a look, and I talk about this some in my guide in terms of the cost. If you take a look at like 4 liters of hexane in comparison to 4 liters of HPLC grade water or methanol, it is cost prohibitive to do the hexane in comparison, right? So you can do it. You have to pass costs along to the powers that be or the client or whoever it might be. But generally speaking, your cost to the bottom line is going to be higher, and the cost also due to having to get rid of the waste in a certain way is going to be higher because there's greater environmental impact on a bunch of hexane that is produced as waste in comparison to a bunch of water that is produced as waste. Okay, so that is going to be it. We're going to wrap up our lecture on normal phase HPLC here. I hope you guys found it useful and you know a little bit more about normal phase HPLC now. So if you found this content useful, I will encourage you to share it with others and like the content, as it will help spread awareness with the YouTube algorithms on what I'm working to teach here. And the bottom line is I'm here to teach you. I want to help you, the viewer, the chemist, the student, the person engaging with my content. Okay, so subscriptions and comments are always appreciated. And again, you can always show your support by buying one of our guides or visiting chemcomplete.com. You can reach out to me. I am Professor Tomney. I have more work to put together for you guys because it's been quite some time. So I will see you in the next one. Take care, everybody. Have a good one.